right? 4 was maybe and 5 was no in our alcohols. Now 5 is maybe and 6 is no. What are some important aldehydes and ketones? Propanone or acetone, nice solvent. Formaldehyde, pungent odor, and we use it to preserve biological specimens. Formaldehyde will cross-link just about anything that it comes in contact with, which is something that we're going to talk about here in a second. Formaldehyde is a preservative that we use, or used to.
Is it a squid or?
That is a gastropod of some sort, yes. I don't know if that's a squid versus an octopus. It's got a elongated back here, so it's probably a squid, but I can't count tentacles versus appendage versus
cephalopod.
16.
Right, but there's, yeah, it's a cephalopod of some sort, yes.
You said gastropod.
Oh, you're right, actually. Yeah, gastropod with snails. Yeah, cephalopod. But yeah, I can't tell whether or not there are tentacles versus arms. That's what it is, tentacles versus arms. Octopus has 8 arms. Squid has 2 tentacles, which are longer than the arms. What I don't know off the top of my head is if it still has 8 arms or if it's down to 6. I don't know. Not off the top of my head. Doesn't really matter in a chemistry course.
Matters to kill them, aren't they?
If you want to preserve something, maybe.
Benzaldehyde is what gives almonds their flavor and therefore smell. Vanilla has that aldehyde group, or the aldehyde up here, right? It's aldehyde because it's a terminal carbon, right? Cinnamaldehyde is what makes cinnamon smell the way it does. You can appreciate the vanillin, or vanillin is a common name for this molecule because what would you call that? Well, we've got an aldehyde as a thing off the side here. We have a phenol group right here, but then that phenol group also has an aldehyde, or an ether actually, because that's an O with another bond coming off, so there's a terminal carbon right there. So the vanillin is an aldehyde with an alcoholic hydrocarbon ring that's also an ether. Can you appreciate how using the IUPAC naming nomenclature for this would get really hairy? So we just call this vanillin. I don't expect you to remember vanillin's shape. You can look this stuff up, but that's these. You guys should be able to, or I can, ask you questions about what functional groups are here.
8 arms, 2 tentacles.
Is that?
8 arms, 2 tentacles.
8 arms, 2 tentacles? Thank you. Alright, on the subject of 8 arms and 2 tentacles, let's take a 10-minute break. Because we've been sitting here for the better part of 2 hours. And I feel like we're not 47, we're not that far. We might, yeah, we'll probably be okay. I warned you guys that when we got into the biochemistry, or the organic chemistry, it was going to get dense.
Interesting.
I get it at some points, and then I kind of lose it, and then I get it again.
Right, well, because it makes sense, but then we're like, okay, I have all of my rules organized in my head, and then you add one more, and you're like, no, it's like the juggler who just gets one too many balls thrown in there, and everything just falls.
And now we're gonna like tie this into like how to solve like formulas and stuff.
A little bit.
Oh no. I didn't think that one.
Oh, I did.
Same.
Yeah, exactly. It's almost, it's like you're in a chemistry class. I mean, really.
I know, right? It's crazy.
I guess so. What did you observe?
Know that we're gonna tie this into solving like some type of formula for
Balancing
ology.
Oh.
Yeah.
You know, if you had it said in
It
still would've happened.
Yeah, exactly. It's still what happened. Yeah. Pretty much.
That's what it just is, so sorry.
I got smart ones because I don't want you teaching us wrong.
Thank you, I appreciate that.
Oh, yeah. Smart Stephanie. Did I used to use that word, chirality?
In what context did you use it?
Which end we're starting from?
Yes. That would be an inappropriate use of the term chiral. Yes.
Okay.
Chirality has to do with the order of constituents on a specific carbon, not which carbon comes first in a invertible molecule.
Cool. Thank you.
Mm-hmm.
But that would be, chirality would be applicable in the term to look like left and right isomers?
Yes.
Because I take the individual.
Well, left and right isomers, in some cases, yes, because you have left and right chirality, which is not the same thing as left and right isomers. Because chirality has to do with the different things that are on one carbon. So it would be chiral isomers for things where we're here or here on a locked carbon. So if you have a carbon chain that's doing this, right? This one right here is going to have two things coming off of it. So one towards us and one away. Okay? And so if this is a chlorine and this is a hydrogen,
Okay.
since that's locked in order, if you inverted them, where you have exactly the same molecule, but now the thing coming out towards us is a hydrogen and the thing going away from us is a chlorine, then those are two different chiral isomers of that molecule.
Because I think I heard chirality reference, I take
And
Nuvigil.
then there's another test on the 22nd.
Provigil, it's a non-addictive,
Yeah, that's
non,
test number 3.
antiretinal based
B week.
Stimulant.
Okay.
Developed for narcolepsy, and necessitate as
And that would be,
whatnot.
uh,
So originally,
and then test
they
number
used to
3
include
was 7.
both isomers
Next week.
and
Yeah,
for
the
research.
15th, right? Or is it?
Found out
Yeah,
it's the left-handed
that's my fault.
isomer.
Which doesn't surprise me because most biology is left-handed.
And so they formulated a way to eliminate the right hand. But I think in the context of they were from the hierarchy.
Yeah, and that because likely what happens is when you're working with a carbon that has a specific substitution, we're actually going to look at something kind of like that. So when you have a double bonded carbon, these two C's here, if you're coming in to break this bond, if this one is a hydrogen, it doesn't matter. But when this one comes in, you're going to break this and turn it into a single bond. And so the question then becomes, of the other two constituents, A or B, the thing that you're trying to insert to attack that bond, like let's say it's a hydrogen chloride molecule or something like that. So you're trying to chlorinate this molecule. Does the chlorine go into A or does it go to B? Because it could do either one. And A, which would create two different chiral isomers.
Okay.
And so A is functional, as this drug that you mentioned, and B is not.
Can I guess that? Are we even talking about sucralose?
No, we won't, but that is another example. But that's actually, I believe sucralose is an example of stereoisomers of like the left-handed, right-handed for the whole molecule.
Right.
As
But
opposed
it's not
to,
a true left-handed sugar though, right?
It's so,
Because it's not flipping the molecule, it's substituting a chlorine
They're worried that
atom
Yeah.
for,
well, in that case, then yeah, it might be a chirality, or it might just be the chlorine itself making it, no, it might not have anything to do with chirality, it might have everything to do with just our enzymes can't digest a sugar with chlorine.
very problematic food stuff. It's 600 times sweeter by weight and volume. So they had to figure out how to infuse it with
Non-sweetness?
air,
Do it, done putting D.
so that it would measure 1-to-1 with sugar. But then the reason it doesn't work in baking is the second you add water, that air disappears and the whole thing goes flat.
I did that for my
Yeah.
homework, I don't know.
that's good.
No.
That's awesome.
It's really good in chemistry.
Alright, so let's get back into this. I was trying to do attendance, but I can't find the page.
Seriously?
I was looking for a quick link to get me back to it, because I can't do it through D2L, I have to be on Cougar Track. And I don't have a, I need to just hotline Cougar Track.
But there's an app for your device.
I've never done that before.
Type it.
Yeah, there's an app for your device.
Like probably Google.
For my phone, you mean?
Uh-huh.
Oh, that, maybe, yes, but I was just using attendance through
That's what
the,
I've been doing.
through the computer itself, which I could continue to do, but
Ever fix the smartphone?
nope, still unplugged.
Do they know about it?
Yeah, I reported it to them.
Did you take attendance?
Was that?
You took attendance already?
No.
Okay.
I did not. I know of 2 individuals that are not here. 3 individuals that are not here. Yeah.
Kelly?
Yes,
She's going through some family stuff.
right. I'm aware of that. Yeah, so, just trying to keep my attendance, I'll figure it out after class, after we're done talking. It just means I have to reload just go to Columbia College and click on the thing from there. Or yeah, get the app on my phone, which might be better and allow me to do it. I'll have to play with that. I was just using the link, but you can't get to the link from once D2L is loaded. All right, let's talk about reactions with these guys. So here we have what? It is a combustion reaction because we are combining a hydrocarbon with oxygen, yes, but what is this specifically?
Alcohol.
It is an alcohol, and the name of that alcohol would be
Ethanol.
ethanol. Right? It is a 2-carbon alcohol.
Yum.
So instead of ethane, it's ethanol. All, not al, but all, right? So, here we have ethanol combined with oxygen to form CO2, water, and energy. So, not just the combustion here, but also in other ways of undergoing different types of reactions. So, this is an alcohol. If we take this alcohol and combine high heat with a little bit of hydrogen, we can convert that alcohol into an alkene. Now we can also force this reaction to run in the opposite direction. Because remember, this right here is exactly the same thing. If we just take this and draw a line right there, we have now formed a position where we can break these two bonds, where that goes this way and this goes that way. I haven't drawn it for you like that before, but this might work as a better way of illustrating that, right? When we have these 4 interchangeable bonds in the presence of a catalyst, we can take the electron density that's here, and they can go down there. The electron density that's there can move up there, and now we have reformed a water molecule, right? And created a carbon chain that has a double bond, which is why we call this an alkene. It would be specifically what? Alkene is the general name for this, but this is a 2-carbon alkene, which would make it make the name for this be ethene, right?
So you said it can go the other way. Why is there only a single directional arrow?
Because this is the way you catalyze this reaction. We can also drive it in the opposite direction with a different catalyst.
So if you put the bottom arrow going the other way, can you list the catalyst underneath?
Yeah.
Okay.
What's that?
Where'd you get ethane?
This right here is a 2-carbon hydrocarbon, right? So if it was just, if all it was 2-carbon hydrocarbon, it would be ethane, right? But this is a 2-carbon hydrocarbon with a double bond, which makes it not ethane, but ethene, right? It is an alkene as a general group, because any hydrocarbon with a double bond in it is an alkene, right? What's the name of a hydrocarbon with a triple bond in it?
Is that the?
That's the YN, which sounds like an I, alkyne, right? Yeah, ethyne, right, yeah.
So after saying methane, you started saying methane for a while. Was the power suggestion, or do you use them interchangeably,
Methane or methane,
or are you an Anglophile?
aluminum or aluminium, whatever.
Doesn't matter.
Tomato, tomato. Alright, so when we're talking about organic chemistry, I do want to point out one thing here, because this reaction, actually in the previous chapter, is where it talks about running this reaction in reverse. It even mentions this reaction earlier when we talk about taking ethene and making alcohol. But when we are doing that, the order of this, like in this particular reaction, it doesn't matter. Because you could do the OH on the right and the H on the left, or the OH on the left and the H on the right, right? But if this was a 3-carbon molecule, if this was a 3-carbon molecule, then it would have to be like this, because that would turn this H into a carbon, right? And then that would have 3 hydrogens coming off of it, right? So this would have started off as a double bond, so let's do this over here as well. Let's turn this into a carbon, a CH3 group right there. All right? Now when the oxygen comes on, we could do it this way, or we could do it this way. Right? But the reason why I'm bringing it up is because it's something that's pointed out in your book, but the slides never mention it, is that it's not going to happen like this. It's going to happen like that. And the reason for that is because the hydroxyl group is going to attack the carbon that has the most derivatives. So it's going to attack the carbon that has the fewest number of hydrogens attached to it, is another way of looking at it, or the most differences. This carbon is only attached to 3 hydrogens and 1 other carbon. This carbon is attached to a carbon, 2 different carbons, and a hydrogen. So it's going to attack the one that's modified in the middle. I honestly can't tell you if that's an important detail, because I haven't looked at the test bank to see whether or not that question's in there about, I don't know how I'd be able to make a test question like that would work versus drawing it. But it's something that's mentioned in your book, and I thought I'd throw it out at you because it's just beginning to peek at a concept that's important for organic chemistry and the synthesis in chemistry of how do we take reactions, how do we take molecules and react them to generate things? What are the rules of how chemicals react with each other? Because it's not all just random. More modified carbons are more susceptible to reactions. And that's going to come into play a little bit right here. So, remember oxidation and reduction when we were first introduced to it? Oxidation is loss, reduction is gain, right? Oxidation is loss of electrons, reduction is gain of electrons. Now that works when we're talking about individual ions oxidizing each other, right? But how does that work when we're talking about these large molecules? And so things get a little bit different. Now, oxidation reactions are the ones that increase the number of carbon-oxygen bonds by the addition of oxygen or by the loss of hydrogen. So here's where the name oxidation actually sort of makes sense. Because oxidation is the addition of oxygen. It's oxygen becoming an even closer friend to the molecule in question. We either add an oxygen with a single bond, or we take an oxygen that has a single bond and we turn it into a double bond. In both of those cases, we would be losing a hydrogen, right? So if we take a normal hydrocarbon and we want to add a hydroxyl group, that would be oxidation, because we are increasing the number of carbon-oxygen bonds, right? But that hydroxyl group has to replace a hydrogen, right? So we're losing the hydrogen off of that molecule. So we're gaining an oxygen bond, we're losing a hydrogen. What about an oxygen that's already there? For it to form a double bond, you have to lose hydrogens. In fact, that would require the loss of 2 hydrogens. One from the oxygen, and one, presuming it started as a hydroxyl group, and then one from the carbon it's trying to bond with, right? We're taking the place of some of those hydrogen atoms. Reduction is therefore the opposite, where we reduce the number of bonds between oxygen and carbon by either taking a double bond and turning it into a single bond, or by taking a single bond and completely removing the oxygen and replacing it with something else. So, here we have a single bond oxygen, right? 1 carbon attached to 1 hydroxyl group. This is a primary alcohol. How do you know that? Because it says it right there.
It's got that 1 degree.
Yeah, it's got the one little squiggly thing, the 1 degree thing that tells you it's a primary alcohol. But why is that? What makes a primary alcohol a primary alcohol? What is the thing that determines its degreeness? How many other carbons is that carbon attached to?
1.
Just 1. Right? That makes it a primary alcohol. So if we oxidize this molecule, there are 2 things that can be done to oxidize this molecule. But what we have to do is increase the number of carbon-oxygen bonds. So here we are describing it as oxidation to where we are turning this from a single bond into a double bond, right? But what are we losing? We are losing this hydrogen right here. Is that it? What else did we lose? We lost another one, right? We lost that hydrogen there, and it really doesn't matter which one of these things I circle, but to keep it spatially oriented the same, we also lost that one. We gained another bond of oxygen, yes, which is a very high energy bond. I'm sorry, I believe I actually just said that wrong. It's a relatively lower energy bond. Oxidation results in lower energy molecules. So, here we have our alcohol, and what did we turn it into? It says right there, but how would you know that? It's an aldehyde, because a hydrocarbon with a double bonded oxygen is either an aldehyde or a ketone. What's the difference?
Terminal and non-terminal.
Is it the end or not? Terminal or non-terminal? Terminal or central carbon? If it's at the end, it's an aldehyde. If it's in a middle carbon, a central carbon, it's a ketone. Can you have a ketone with only 2 carbons?
No.
No, because there are only 2 carbons. Either one of them is at the end, right? So, aldehydes can then further oxidize to produce carboxylic acid. So here is our aldehyde. We are oxidizing it again because the other thing that you can do, if you can't turn a single oxygen into a double oxygen bond, you could also just add a new oxygen. So here we are replacing that hydrogen with a hydroxyl group. Why is this not still an aldehyde? We have a double bonded oxygen attached to a carbon at the end. Because it's not the H, because there's another oxygen there. For it to be an aldehyde, that's why there was that additional little part of that definition for aldehyde. To be an aldehyde, the third constituent of that terminal, or I should say the fourth constituent, because one has to be a carbon for it to be terminal, right? The other 2 are the oxygen, so the fourth constituent to be an aldehyde has to be hydrogen. If you replace that with anything else, it's not an aldehyde anymore. It's something else. If we replace that with a hydroxyl group, now we have carboxylic acid. This is a functional group of biological acids. Because that guy right there, remember when I mentioned the whole, remember a 6-carbon cyclic ring? Remember there's a lot of ways we can draw that 6-carbon cyclic ring, and one of them is with that circle in the middle. Because those double bonds aren't literally between just those carbons. They're also they can flip back and forth. Well, guess what can flip back and forth right here? That double bond right there could also be drawn kind of like this. Delocalized between both of those oxygens. Guess what that's going to make that hydrogen feel like? And not very loved. So what could that hydrogen quite easily do? Leaving us with a negatively charged oxygen and a positively charged hydrogen ion that could react with water to form a hydronium ion, right? Thus, hydrogen donor, thus, acid?
Is there music playing? It could be the voices in my head. Is this...
Perhaps your soundtrack is just increasing in volume.
That'd be awesome. Is this Apollo 13, when they can't scrub, doesn't it start producing carbonic acid in the blood?
I don't think that's the same thing. Your blood starts producing carbonic acid. Yes.
Okay.
And that's just because if there's too much CO2 in the air, the CO2 pressure in the blood gets too high, and eventually that saturates the carbonic acid buffer in the blood, and then the pH actually starts rising, and then you die. So, yeah, not this. Different thing. This is still oxidation though. Why? What have we done? Now, granted, this is a gross oversimplification, because that little arrow there that tells you oxidation, we could go into the details of what it actually takes to make that happen, but we're not. We're just saying, look, we can oxidize this. And by doing so, we have done what? We have added another oxygen to this molecule. Oxidation of hydrocarbons with respect to this means the addition of more oxygen, more CO bonds, either by turning a single bond into a double, or by turning a double bond, or by getting rid of a hydrogen and adding in another oxygen. Now, I want to ask you something. This goes a little bit beyond where we need to be for this chapter, but I want you to appreciate something because they have color-coded this beautifully for us. So, what happens when we take sugar and we oxidize it down completely in a combustion reaction? What do we get? Energy and CO2 and water. Where does the water come from? The water comes from knocking off this hydrogen and reacting with other water molecules that are already there in the system. We make CO2 by taking hydroxyl ions from water and combining it. So remember the way that we do this, we're adding this right here, we are swapping out this hydrogen for this hydroxyl group. But how could we further combust this? What could we do to further increase the oxidation state of this molecule? Let's make sure it's not literally right. Okay, good. What could we do to further increase the oxidation state of this molecule? What does oxidizing hydrocarbons mean? It means increasing the number of CO bonds, right? We started with just one, all the way back here. Just one. We oxidized it in one step. Now we have two. Over here, we have two. We oxidize it one more. We add on another hydroxyl group. So what could we do to further oxidize this molecule?
Attack the second carbon.
Well, we could add more hydroxyls here, yes, but that extra addition is actually a little bit harder than simply making this a double bond, because remember, this is already a little bit of a double bond already. So what if we want to take this oxygen right here and attack that carbon, lose this hydrogen, to form another double bond? So instead, we go from here down this direction to make a carbon that has a double bonded here and a double bond here. Well, there's a problem because this carbon's already still attached to this guy over here, right? So if this one's attacking here, then this bond right here has to go away. This bond has to go back towards that. That electron density has to go back towards that. So in other words, what we just did is we broke this bond and we broke this bond, everybody see it? To form a new double bond right there to make this. Well, what is that? It's CO2, carbon dioxide. What's one of the products of combustion of carbohydrates or hydrocarbons? We did it again. CO2. Continual, repetitive addition of oxygen. Oxidation of hydrocarbons. This is what happens when you burn wood in a fire. This is also what happens in the citric acid cycle in your mitochondria. Except that we have enzymes that are chaperoning all of these reactions. And every time one of these carbon-carbon bonds is broken, it gives off a little bit of energy. And we can capture that energy in the form of NADH, FADH2, or ATP. Like I said, this gets squiggly because it's getting ahead of ourselves, it's getting beyond what we're going to need to be worried about. But I wanted to point this out. One more oxidation step and we would have just popped off the CO2.
So is charcoal from doing the easy work ahead of time and reducing it just to the power of dense?
Honestly, I'm not really sure about, because the way you make charcoal is by burning wood.
In the
But
absence of oxygen.
But yeah, but you don't want to burn it. You don't want to burn it all the way. You want to burn it to a point where it's ready to further react, but hasn't yet reacted. And that would have a lot to do with the energy states of some of those intermediate molecules, because it's like, well, it's 12 steps in the TCA cycle, but it's a lot of steps in normal oxidation of the carbon that's in wood, and I don't know what the energy levels of all those things are. But presumably there would be a point in there where there's one with a really low level of activation energy, meaning it's ready to get started really well. But it's still not going to have as much energy as the wood that it originally had to. Because it's the exothermic reaction that gets us there. Otherwise, making charcoal would require us adding a lot of energy from something else, which we do by burning wood in the first place, but we're losing a lot of that energy.
But when we're burning wood, isn't the combination of the higher energy and the lower energy input at once, isn't that actually decreasing the overall?
I don't know if I can answer the question because I'm not very familiar with how we make charcoal specifically.
We bury it, we start a fire at one end and we let it progress underneath the earth, and it takes out the easy work, and well, I guess it takes out the hard work, and what's left is that
Right, readily combustible material.
yeah.
Right. But that still might have less energy than the beginning products, but the energy of activation for the leftover reactions is probably less.
Yes.
So it takes less to light it, to finish it, than it would have before, and so that's why it's a good fire starter, is because there's less energy per gram unit in charcoal, but burns hotter and faster, because we've gotten rid of a lot of the other reactions that are harder to do.
Yeah, that's what yeah.
That would be an educated guess as far as why that works that way. So, that's that. We can also take secondary alcohols. How is this a secondary alcohol? The OH is in the middle. Yeah, but the OH can still be in the middle in a tertiary alcohol. Excuse me. Yeah, tertiary alcohol too. This is a secondary alcohol because the carbon that's attached to that alcohol, how many carbons is it attached to? 2. That central carbon, the one that's holding on to the hydroxyl, making it an alcohol, how many other carbons is it attached to? 2. That makes it a secondary alcohol. Because the primary alcohol was primary because that carbon's only attached to 1, right? So, here we have our secondary alcohol, all right? We can oxidize that by creating a ketone. What would this be, by the way? Name this. There's 3 carbons.
No.
Propanone. Propane. 3 carbons is propane. Get rid of the E at the end and replace it with O. Propanone. 3 carbon ketone. Propanone. It really is a simple set of rules, guys. We're just getting them all thrown at us right off the bat. There's a lot to remember. What would this be? Name that one for me. Come on! Half the work's already done!
Propanol?
Propanol, but you need to finish it. There's more than one place you can put the hydroxyl in propanol. 2 propanol. Yeah. See? You got this? Not written down? You don't believe me? You got it! So here, we are oxidizing 2-propanol to propanone. How do I know it's oxidation? How can I tell that it's oxidation? Because if I showed this to you on the test, well, one big clue would be if I put a big box with an O over it, that tells you it's oxidation. But even if I didn't, if I asked you, is this oxidation or reduction, would you be able to tell? How could you tell?
Because of the O right there.
Because of the O right there! Well, Oxidation is increasing the number of CO bonds, right? How many do we have over here? 1. How many do we have over here? 2. Therefore it is oxidation, right? This is a tertiary alcohol, but you'll note that there is no product. Why not? Because there is no hydrogen to attack here. In order to turn that carbon into a carbon double bond with that oxygen, we have to get rid of that hydrogen, and we also have to get rid of another hydrogen. Ah, crap! We can't. There's no other hydrogen. It can't. It's not going to steal. Because this guy here is attached to that carbon, and that carbon. It's got to steal something else off of what that guy is attached to. And it can't do it. Now, it can be done in a situation like this, but it can't be done in a situation like that. Once again, that whole popping off the CO2 thing, that's an oversimplification and getting ahead of ourselves, but I just wanted you to see conceptually how that works. How it is that we combine oxygen with hydrocarbons to make CO2 and water. We can't oxidize a tertiary alcohol because there is no other hydrogen to attack on that carbon. So, methanol. Methyl alcohol, highly toxic, makes you go blind. Windshield washer fluid, sterno, paint strippers. We can readily oxidize this methanol, can be readily oxidized inside you. It's rapidly absorbed by your body and then oxidized from methanol to methanal, otherwise known as formaldehyde. And that then gets further oxidized by replacing one of those hydrogens with another hydroxyl group to form methanoic acid, or formic acid. And that's some nasty stuff. Toxic stuff. Methanol is nasty not because of some sort of inherent property of methanol, but because in your body, the enzymes that are already there can quite easily oxidize it. And the end product of that is something that is inherently toxic. Ethanol can also be oxidized. But what's the end product of the oxidation of ethanol? CO2 and water. The oxidation of methanol is methanoic acid. At least in your body. Ethanol, actually a depressant. It kills or disables more people than any other drug on a daily basis. And it has been legal for the entire history of the United States, minus about, what was it, 15 years? That's getting borderline close to discussion about the need to legalize or criminalize certain things for the benefit of society. Let's not talk about that in your chemistry course. We can analyze how much ethanol is in your system via a breathalyzer quite easily. Social drinkers metabolize it at 12 to 15 milligrams per deciliter, but an alcoholic will metabolize it at a much higher rate. This is why alcoholics have to drink more to get drunk and drink more to stay drunk. What about thiols? Thiol can oxidize as well, except here's where once again the term oxidation isn't quite so perfectly named, because the oxidation of thiols has nothing to do with adding oxygens. But it does do something that is very, very easily recognized. Oxidation of thiol groups comes in the form of forming disulfide bonds. Disulfide meaning two sulfurs, disulfide. And so when we take a thiol group, what we're doing is we're allowing those two groups to come together, and they will react with each other and form a covalent bond between the two groups. This is actually a critically important reaction for life, because a lot of the proteins that you have in your body, their shape is held together because of these disulfide bridges that are cross-linking the different parts of the proteins to hold the protein in a very specific shape. But if we change the energy state of your cells and reduce that bond, i.e. break that bond, by moving in the opposite direction, then that lock is no longer held in place. And the protein can shift its shape and therefore lose its function. Your cells will change the oxidation state of your membranes in order to encourage the formation of these disulfide bonds, or to encourage the breaking of these disulfide bonds as a way of turning some of the enzymes in your membrane on and off. But it has everything to do with the oxidation of that disulfide bond, or oxidation of the sulfide groups into a disulfide bridge, or a disulfide bond. The cross-linking of disulfide bonds is what gives your hair its structure as well. Your hair is a protein matrix. It grows out of your body. It is made out of protein. In the same way that beef is made out of protein. In the same way that your muscles are made out of protein, and a lot of other things too. Your hair is a protein extracellular matrix, and the strength of it has a lot to do with the disulfide bonds that are cross-linking the hair, the proteins that make up your hair. Holding them in place as a big, huge lattice. Somewhat out of place, this particular slide, since we went from talking about alcohol to thiols and then right back to alcohol. Well, whatever. Effect of alcohol on the body, blood alcohol levels by mass by volume, 0.025, dizzy or talkative, 0.05, euphoria, loud talking or laughing, 0.1, loss of inhibition, loss of coordination, legally intoxication in most states, in fact, 0.08. I believe is the cutoff in a lot of states now as well. I think in Missouri it's 0.08, isn't it? Yeah. 0.2, highly intoxicated. 0.3, unconscious. 0.4 to 0.5, coma or death. This is mass by volume. How much was that hand sanitizer again? Granted, it was volume by volume, so not exactly the same thing. We can't. It's a little bit of an apples to oranges. Hand sanitizer was 60 to 70%. Volume by volume. 0.4%, and you're dead.
But well preserved.
Quite possible.
Pickled.
You need a little bit more than 0.4 to be pickled. But yeah. Alright, so let's talk about some interesting things that we can do. Interesting ways that we can take advantage of some of the specific chemistry or organic chemistry and inorganic chemistry in order to use it as a way of testing what type of organic molecule we're dealing with. So there's this thing called Tollens test, or Tollens reagent. It contains silver ions. And those silver ions can oxidize aldehydes, but they can't oxidize ketones. So here is ethylaldehyde, otherwise known as ethanal, right? Acetylaldehyde. 2-carbon aldehyde. If we add Tollens reagent with a couple of silver ions, it can oxidize that. Now granted, once again, we are skipping over some major chemistry here. We're just saying an oxidation happens, like we're sprinkling pixie dust on it. It's oxidized. I can accept that. So, if we oxidize this aldehyde in the presence of Tollens reagent, what we get is a silver matrix as a solid that precipitates out in a special form that makes it look like it has a mirror shine. It's the same type of mirror shine that we use to literally make mirrors.
That's the term.
But it also produces ethanoic acid. So what it does is it's oxidizing this molecule by turning an aldehyde into an acid, by adding an extra oxygen, because that's what oxidation is with respect to hydrocarbons, right? It does that via an aldehyde, but why not a ketone? What do we have to be able to do to oxidize that terminal carbon? What's being removed, replaced with the hydroxyl group instead? That hydrogen. We're replacing that hydrogen with a hydroxyl. I don't want you to think of this in terms of, we're not taking that hydrogen and saying, could you please step just a little aside, someone needs your seat. Could you sit in the seat right next to it? We're not putting a hydrogen in the middle of the carbon and the hydrogen, or excuse me, we're not putting an oxygen in the middle of the carbon and a hydrogen. We are replacing a hydrogen with a hydroxyl. That's not obvious on this slide, but I wanted to point it out. So the only way that we can add that hydroxyl group is by removing that hydrogen, by attacking the relatively weak carbon-hydrogen bond right there. Well, what's a ketone? Where is that oxygen double bond in a ketone?
Non-terminal.
In the middle. Which means the carbon that it's attached to, what are the other two bonds to other carbons? There is no hydrogen to attack. So we can't oxidize it. That's not to say it can't be done. It just can't be done by this. Everybody follow? So Tollin's test is a way to determine if you have an aldehyde. If you get an otherwise bluish solution, if it turns to a metallic silver, then whatever you have in that solution is an aldehyde. If it doesn't, then it's not.
Does it differentiate if you have both aldehydes and ketones? Or is it just...
No, it does not. It would tell you that you do have aldehydes.
Right.
If you also had ketones, it would not tell you that, but it would tell you that you do have aldehydes.
So is there a second reagent?
Thank you.
Sort of. There are other ways to find out, yes. Benedict's test uses copper ions, and it reacts with aldehydes that have an adjacent hydroxyl. So this is 2-hydroxypropanal. This should tell you something. Because we haven't discussed this rule. Why isn't this I don't even remember the name for the functional name for that off the top of my head, actually. Spacing. Why is this not an alcohol? Why does the name not end in OL? Why does it end in AL? Quite simply because the aldehyde trumps the alcohol. So this is an aldehyde with a hydroxy addition, not an alcohol with an aldehyde addition. Follow? Mm-hmm. So there's kind of an order of operation. Like in math, you always multiply and divide first before you add and subtract. So this is 2-hydroxypropanal. We can react this with Benedict's, and it will create a brick red solid by oxidizing that hydrogen right there and turning it into another another carboxylic acid functional group. It doesn't get rid of that hydroxyl, but that hydroxyl is necessary. Once again, this is because of odd biochemistry that we're not going to get into, but it has something to do with the bending of this carbon. But that hydroxyl is necessary in order for another hydroxyl to come and attach right here. If that hydroxyl is not there, then these two copper ions just sit there and they do nothing.
Why red, not green? Green, green. It's copper rust.
Right, copper oxide you would think you would expect to be green. I don't know. Might have something to do with the oxidation state of copper in this case. But yeah, brick red. Here is Benedict's solution before you add heat. Here's Benedict's solution after you add heat. What's it reacting to? This is D-glucose. And after reaction it becomes D-gluconic acid. This guy up here, the aldehyde, became an acetic acid group. But it could only do so because of that hydroxyl right there. Benedict's test is a test for sugars. Specifically, it's a test for simple sugars. Monosaccharides and disaccharides. Because it can take the aldehyde that is the linear sugar, and if there is an adjacent hydroxyl, it can oxidize that molecule to turn it into something other than a sugar that is now gluconic acid instead of glucose. Benedict's test is a copper test for the presence of sugars. But really, it's just a presence of an aldehyde with a hydroxyl that's one carbon away. Because that's what's happening, right? This is an aldehyde, and there's a hydroxyl one carbon away. Any linear molecule that is an aldehyde with a hydroxyl one carbon away will react with Benedict's and become an acid. Benedict's, which is simply a copper solution, a copper salt solution, will oxidize that carbon right there by changing that hydrogen bond into a hydroxyl bond. But it can only do so if there is another hydroxyl one carbon away. Once again, why would this not happen? I suppose the rules are a little bit different there. This doesn't happen for ketones. Because if this was another carbon, we would not be able to break that carbon to replace it with the hydroxyl. This attack requires an available hydrogen to be replaced by a hydroxyl group. And that only occurs in aldehydes. Aldehydes and ketones are both reduced by a sodium borohydride solution or hydrogen solution. Reduces the number of carbon and oxygen bonds by the addition of hydrogen or the loss of oxygen. But that takes catalysts like nickel, platinum, or palladium. You have to have something that can interact with that electron density, break it up a little bit, throw in some extra hydrogens. This is reduction. Not to be confused with all the previous slides where we've been talking about oxidation, right? Reduction, when we're talking about organic molecules, hydrocarbons, means that we're doing what? Not adding CO bonds, but decreasing them, breaking them, taking them away. So we take a CO double bond, and we break it and add some hydrogens. We take a CO single bond, and we remove it and add some hydrogens. See, here we have propanal. It's an aldehyde, right? Because we have a terminal carbon. We can, in the presence of platinum, I think actually, platinum, with a hydrogen gas, the metal acts as a catalyst, and we are breaking that double bond and adding a hydrogen to both the oxygen, but also adding it to this carbon down here. So now we have one propanol. We can do the same thing with a dimethyl ketone. This is propanone. 3 carbons, but it's a ketone because we now have our double oxygen in the middle, right? We can not oxidize, but reduce that by bringing in hydrogen in the presence of a metal catalyst, and we attach that one hydrogen to the oxygen, one hydrogen to the carbon. We now have a secondary alcohol. Why is it a secondary alcohol? How many carbons are attached to the carbon that has the alcohol functional group?
2.
1 here, 1 there. 2. Secondary alcohol. And that's it. That is chapter 12. So a lot on reduction, a lot on oxidation, and it really need to be a reduction.
It's okay.
Yes. That's okay. All right. So it's 8:11, and it is frowned upon that I let you guys out super duper early. But I also see a lot of like I'm only barely awake stares. So I think we're just going to call it for the night. Are you okay with that? You guys were paying for this, so you know.
Yeah, that's really supposed
Next
to
week,
be.
we're going over chapter 12 again. Right? Because it was kind of in the syllabus. So we're kind of going over chapter 12.
I don't know.
Are we going to chapter 13?
We'll be moving on to chapter 13.
Okay.
We might, because I think I changed it to where it was 1 chapter a day. But I might have, I know that I intended to maybe give myself a little bit more time for organic chemistry because this is, as is evidence, really kind of heady stuff, right? So what we may end up doing is go back and look at chapter 12 and chapter 13 practice problems and work through some of the nomenclature on those. But we might jump to 13 first and get it out of the way, and then kind of come back if there's time. Because what I don't want to do is get behind moving forward, but I also don't want to effectively not have class one day because we don't have anything to talk about. So there's a lot of stuff here. One thing I will point out, I noticed this is a mistake that I made when I assigned the homework last week. And I almost changed it today, but then I was like, no, it's my mistake, not yours. So for those of you who finished the homework that had been out in time, congratulations. Hopefully you did well.
I just want to
extra week.
say it.
Right. Exactly. So I was like looking at it and I was about ready to send emails out to a couple of people who hadn't done it yet, being like, you've only got a couple of hours. And then I realized, no, actually you've got a whole week. And that's when I almost changed it and then realized, no, that would be mean. It was my mistake. So if you haven't done it, or if you still have another option there, like if you haven't done your second attempt, you've got another week to look at your homework. There will be another one opening up tomorrow morning-ish. I don't have a solo movie tonight, but I also don't know how easy it's going to be to make some homework questions from the end of the chapter stuff. There might be a lot of importing pictures and stuff. So it should open tomorrow sometime, and it will be due, not 2 weeks, but in 1 week, because I made sure to fix that for the future ones. But yes, technically, if you haven't done the homework that was due today, you technically have a whole other week to do it.
So is that why you don't correct other errors? Like,
And then I
I'll
just
bring her-
accepted it. Because I was like, I'm not taking this.
Wow, that bone, you just keep
No,
chewing, keep chewing.
I'm waiting for something else to come along. Because that one's getting old.
Ah, I see.
I saw that, like, that it was due the 7th, and I was like,
Uh-huh.
he's wrong.
Yes.
There's something going on.
I was looking for the missing homework assignment in the middle.
I totally did that wrong. I don't know like what I was doing.